Torsion of shafts. Okay, so torsion of shafts is, or can be elaborated a lot more and in a lot of detail. But I'm going to be just covering the very basics over here, so that you're familiar with torsion of shafts are, and that you can sort of get an idea of what it entails, and if need be, and you need more information about this, then obviously you can do further research about it. Okay, so we've got this type of scenario over here where we've got some wall that's securing some shaft. There's some torque acting on it. The shaft is a certain length and the shaft is a certain diameter. Okay, now in this specific example, I'm using a wall to make it rigid so it can't basically move over there at that end. And if I've got to demonstrate it with this piece of brace stick again, I'm securing it over here, and I'm trying to act some or either rotational torque on it, and as the torque happens, it means that the shaft is going to start twisting, and as it starts twisting, it's going to start getting narrower, and eventually you'll find that it will even snap. Okay, so or it gets thinner and it snaps. Okay, so that type of system will actually then happen. And let's have a look at it in terms of a noodle that I've got over here. So with this specific noodle, I'm going to keep it secure on this side as it is in this diagram, and I'm going to start twisting it. And as I twist it, it's going to go, and then eventually it's going to snap. Okay, so that gives you the idea of what the torsion of shafts are. Now the torsion of shafts can be also often associated with motor shafts. If there's some torque on a motor shaft and the motor is spinning, and there's some other power in terms of the motor spinning, that is going to cause that specific shaft is going to have obviously some torque on it, and therefore there's going to be some torsion acting on it. Okay, so let's have a look at it in terms of a few equations that you need to be familiar with. Okay, so firstly, if you're looking at shafts, there's what's known as polar moments of inertia. And this is represented by the letter J. And that's equal to pi d to the power 4 over 32. So that would be for a solid shaft as we've got over here. But often you do get shafts that could be a tube. Okay, so in those type of scenarios, polar moments of inertia J is equal to pi over 32 multiplied by the outer diameter to the power 4 minus the inner diameter to the power 4. Okay, so that's for a tube scenario. The equations for torsion of shafts are indicated in this box. Okay, so we've got T over J is equal to 2 times tau over D, which is equal to E theta over L. Okay, so T over here is the torque or the twisting moment. And remember, torque or moments is equal to the force multiplied by the distance. We've got J, which is a polar moment of inertia, and we've actually just looked at the formulas for the polar moment of inertia over there. Remember, E is equal to the modulus of elasticity, something we've covered quite a few times now. L is the length of the shaft. Okay, so like in this example, it would be the actual length of the shaft. And obviously, if you look at this equation, you'll see that it is inversely proportional to the torque. Your length, the longer it is, you might find that it's going to be easier to actually snap. If it's a shorter one, it might be less difficult. Okay, so we've got tau, which is our shear stress. Remember, stress equal to force over area, and we also looked at the shear stress type of scenarios, where the shear stress, instead of having a little normal stress symbol, it was in this specific tau symbol. Then D over here is our diameter of the shaft, and theta over there is the angle twist in radians. Okay. Then some other formula that might be useful, especially when it comes to motors. P is equal to T multiplied by omega. Okay, so P is the power transmitted to the shaft. T, we know that's the torque, we've seen that already. Omega is equal to the angular velocity of the shaft, so the speed of that the shaft is going at, and N is equal to the revolutions per minute. Okay, so that is where we come to the second part of this formula, where power is also equal to 2 times pi times N multiplied by T over 60. Okay, so basically just took that angular velocity of the shaft and made it in terms of revolutions per minute. Let's have a look at an example as to how what type of thing you would need to be calculating. Okay, so a 20 millimeter diameter shaft of 500 millimeters in length has a 20 Newton meter torque acting on it. We're told that E is equal to 200 gigapascal. What is the max angle twist that will be observed? Okay, so if you remember from the formula that we just looked at, T over J is equal to E times theta over L. Okay, now remember as well, so if we want to make now theta the subject of the formula, therefore theta is equal to T multiplied by L over JE. Okay. Now remember that with J, which was our polar moments of inertia, that was equal to pi d to the power of 4 over 32. Okay, that's for a solid shaft though. Okay, so looking at this formula again, for the angle twist, that's equal to, okay, so T is our torque, and we're told that 20 Newton meters acting on that. Okay, so we've got 20 multiplied by the length. The length we are told is 500 millimeters, so that's multiplied by 0.5. Divide by J. Now remember, J is pi d to the power 4 over 32. So I can just complete that over here. So that's pi multiplied by d. D, we are told, is a 20 millimeter shaft. Okay, so that is 0.02 to the power of 4. And then that is also divided by 32. So that 32 would come to the top. So that's multiplied by 32 over there. Okay, and then we've got E, and E we are told is 200 gigapascal. Okay, so that's multiplied by 200 times 10 to the 9. Okay, so we calculate that, and we find that therefore theta is equal to 0.00318 radians. Okay, now that we've calculated that, what is the power transmitted if it rotates at 90 RPM? Okay, well, power is equal to torque multiplied by omega, which is equal to 2 pi n multiplied by torque over 60. Okay, so that is equal to 2 pi multiplied by n. N is speed in RPM, so that's 90 RPM. So we've got 90 over there. Multiplied by a torque. The torque we told is 20 newtons, or 20 Newton meters. Okay, so multiply by 20 and we divide by 60. Okay, and we calculate that, and that is equal to 188.5 watts. Okay, so that was an example. Again, this is just a brief overview of what we had to look at now. Like I mentioned, I haven't gone into great detail over here. It's just an introduction in terms of torsion of shafts that you need to be familiar with. You need to be familiar that there are torsion on motor shafts especially. And these are things that you just need to keep in mind whenever you do your designs. Obviously, as I mentioned, this is a science on its own. You can go into it into more greater details. When it comes to motors, you'll be able to associate it in terms of how the internal mechanisms of the motors are working as well and stuff. But what we want to see over here is that there is some torque. Whenever there's some torque on a shaft, obviously that is going to cause some twisting motion. The length is important, and these are essentially the equations that are the ones that you will really be looking at for what is, for the very basics when it comes to the torsion of shafts.